Okay, so we have Liam O'Sullivan, Chad Riley, and Alfred Wojciechowski from CBT here in Boston, Mass. And we're going to run through the work we're doing with modeling and simulations and use the Fitchburg State University Science Building as a case study. So there'll be 4 parts, but as you can see in the slide, that we'll run through with tools, the project itself, the idea of collaboration, and then the focus on IES software and how we've used it in greater detail. So the Fitchburg State Science Project is a just over 100,000 square feet of construction. 55,000 square feet are brand new. About 50,000 square feet are renovation. Here in the United States, it's targeted for the elite silver level, which is mandated by the state of Massachusetts for all of the state buildings now need to be sustainable with a minimum level of elite accreditation. To take you to where Fitchburg is, here's a map of the United States. We're in the Fitchburg State University is in the northeast part of our country, which means it's primarily in a heating season, although during the summer we do experience some dramatically hot temperatures, so cooling is important during the months, specifically around July and August. This is a map of the university itself. We have the quad area and the science building. You can see in color showing the different labs and the organizations. The building is facing south, east, and west, so it has major exposure to the east and west, but also has a substantial component of the building facing south. The design of the building is uses insulated metal panels, double layer of glass, masonry, so punched openings as well as curtain wall. You can see in some of the sections that we have some very tall floors for the lab spaces, and then the existing building has much shallower floor-to-floor heights. So looking at how CBT works, we are evolving as a firm, and the evolution of the firm is really based on evidence-based design, as well as building information modeling, BIM. So we are moving forward with that type of attitude, which means that we're doing work in 3D visualization. So using 3D to communicate design, and we use software packages like SketchUp, Photoshop, Revit, Navisworks, as well as physical models. We also see that being able to have information captured in our drawings is important in how it's sorted. So Revit is the main platform that we're using. And the biggest component that we've added to our work and how we're working is simulation, so building components and elements. And we're using Ecotech and IES to achieve those simulations. So on the 3D visualization, very early on, we're doing quick drawings that are 2-dimensional that quickly pop up into 3-dimensional drawings so that the user group can see what they're doing and getting, and they can quickly respond to programming needs. Simultaneously, we're working in bringing Revit into the early stages of programming and into schematic design, and being very, very specific about each room and its component. And we're always going back and forth between what was in a study area and what was in the schematic design on the plans, what the differential is. So we're tracking all that information and getting a feedback loop from the users as well as the client in terms of staying on target for their space needs, their use needs, as well as their cost requirements. This shows you depictions of our design process where we use SketchUp in the upper montage of building in process, and then also using AutoCAD drawings that get pasted up into three-dimensional depictions of the building so that you can see it from different viewpoints. And again, this is about communicating with the clients, being for them to be able to understand what's happening on their project. And as we move through, we're using BIM, Revit, the Revit platform to create three-dimensional drawings right from schematic design. But these next slides show our work with the structural engineers as they're developing three-dimensional drawings, mechanical, electrical, fire protection, as well in 3D. And we're working with lab designers. For example, this lab designer is in California, so we're sharing information across the continent. Our structural engineer is also in another state, so most people are not locally situated, and the information is being shared through the Revit model and using Navisworks as a reader. So this is a colorization, but these are our part of our working drawings for the Fitchburg project. And this shows some cutaways of the construction documents for the project. And then we also take construction documents and we'll change the color and change some of the lighting and use them as presentation tools. So the process of simulations, environmental simulations, has been of interest to us because it helps us understand how we're how we're thinking about a building form, skin, and taking a lot of the knowns that are in our minds when we start off on a project. So we use Ecotech very early on to just generate some basic understanding of some form and massing, how it relates to the specifics of the climate that we're in. So for example, this one's in northeast United States, but we have projects in Saudi Arabia, very dramatically different climate issues, and so orientation and just exposure become important. So we found that Ecotech's a good tool very early on, but ultimately what we were interested in is developing the design further. And so this is where the IES software becomes the primary tool for our simulation. So we leave schematic design and start early schematic design, and then start jumping into IES software to look at wall assemblies and how light's penetrating and heat, and that starts occurring at the end of schematics for us. Chat?
So the real core of our discussion today is going to be focused around the simulations that we were using with the IES, but we want to take just a moment to discuss the team process, because for a truly integrated design process, you need the key participants, the key design team members, working together and generating information early on in the process. And so the primary players there are the mechanical engineer who's doing the design of the systems, and the commissioning agent who is going to be seeing the fine-tuning of the systems, and then working with the owner or the user group to hand over the building and make sure that they know how to actually maintain it. And then also, and especially in the United States with the rise of the LEED rating system, an energy modeling consultant who is running simulations and validating or confirming the energy reduction targets that are set early on in the process. So in the Fitchburg process, our MEP engineer was working early, coming up with creative ideas, certainly relying on their experience in ways of saving energy, but they're also the one that has to deal with some of the constraints of the existing building. So in our case, where we're doing an addition onto an existing building, and the existing building was going to be maintained and occupied during construction of the addition, the new MEP plant had to be contained entirely within and on top of the addition, so that it would be up and running and functional when it came time to switch over to the addition. In addition, we had some concerns about putting any additional load on the roof of the existing building to avoid some seismic upgrades. So this image here just shows the reality of what they have to deal with as they're working to optimize the systems. Bringing the commissioning agent on board early on is critical, because as the ones who are seeing the systems through to the operations and getting run efficiently, they need to have buy-in as far as what the basic idea, the design concept is for the systems. But they're also quite a valuable resource in looking at benchmarking and different criteria. So in our case, they looked at other state universities that were developing science projects. They looked at Labs 21 and a number of other peer institutions to find out, are we pushing the right envelope, are we lagging behind, or are we way out ahead of where other comparable institutions might be doing. Then in addition, with the energy modeling consultant, they're primarily focused on MEP systems, but they're measuring against baselines and targets. And so this diagram in the top right shows something very early and schematic before there's really any sense of exactly what the systems might be. And we see a lot of green bar charts to the left of the baseline, which means that we were not yet achieving targets in those. And the goal is that by the end of the construction document period, to have all those things swinging around and being to the right of the baseline. So in order to supplement the work we were doing with the energy modeling consultant, we wanted to take a more active, proactive role in simulations and modeling so that we could get data in real time as we're designing the building. We weren't comfortable with a more traditional approach in which you send out a milestone set of drawings for cost estimating, for energy modeling, and then when you get the results 6 or 8 weeks later, it's really too late to incorporate the best and the optimal design. So if the project is working well and the process is through this process, there's a tremendous amount of ideas and data that's being generated, and an ability to organize and track that and find out which are the priorities and make sure that we've accommodated the best ideas that the team has come up with. We need organizational tools like this chart, for instance, where we've grouped ideas for energy savings into different kinds of criteria and categories for easy tracking. And so that really leads us into the energy modeling we were doing ourselves. This is just kind of an overview of the range of topics that we were looking at. As Alfred noted, we were primarily focused on thermal issues, on solar issues, and on daylighting issues. And the next series of modeling simulations we're going to bring you through, we'll show you through that. And what we were using then is our own simulations to find the good, better, and best solutions, incorporate what we thought was the best solution, and then having run the simulations, rather than waiting for the results, we were providing the data to our energy modeling consultant to validate that what we thought was the best approach to take was in fact the right route to go. So with that, we'll get right into our energy modeling. A key piece of it really is getting the appropriate model. On the left-hand side, you can see our Revit model, and the goal of that piece is really to be a piece of virtual construction where the mullion patterning and profiles look like mullions. Brick shells look like brick shells. Even getting into the labs, the gas fitting on the lab bench looks like the right gas fitting. That's the basis for design. When you're dealing with an energy model, that all really needs to be streamlined right down. Really the core things that are critical in the energy model, first is the location and the surrounding context, but then it's really layering up a series of spaces and adjacencies and planes that have different properties. So the model is simplified to shading elements and enclosing elements and adjacencies, and we'll take you through a series of developments of those to see how the pieces interact with one another. So the first set of experiments that we ran had to do with the site context. When the initial base model was developed in the Modelit software that comes with IES, we also wanted to look at the surrounding context. So the first thing we did was to import some of the weather data from a nearby airport. So we were simulating something that was extremely close to our actual conditions on the site. And we also knew from our experience on the site that there's an extremely large hill due west of our project site with a large ridge line that ran right parallel with our north-south orientation. And initially we weren't sure if that hill would have any impact on solar gain, either beneficial shading in the summer or cutting out light that we might want during the winter time. So we ran a series of simulations and found that for the times that we're occupying the building, there really was no impact from the hill. And so as a result, we were able to discount that element from our future simulations. Had we been in a dense urban situation with high-rises or other things that might cast shadow or blaze facades that might reflect additional light onto the building, that would be a key thing to take into consideration. But in our case, the row of deciduous trees that we're intending to plant right in front of the building are a small element as compared to the hill, but by being in close proximity, they're actually going to have a larger impact on the building than the hill will, which is quite further away. I'll turn it over to Liam now for discussion of the building envelope simulation.
We used IES to look at a number of specific components within the building envelope and built up different assemblies, some of them standard within IES and some of them custom, where it was fairly straightforward to go in and modify the assemblies to meet what the local construction practices are. And we ran through these simulations on a building-wide basis to see how they would compare in terms of the potential energy savings that we would realize, and then work with our energy modeling consultant to evaluate what the actual projected costs would be of any savings versus our initial outlay for materials. The first of these we looked at was the exterior building insulation. One simulation was run using the code required minimum 2.5 inches of rigid insulation, and we compared that to a simulation where we ran it with 4 inches of insulation, which was a 20% above code increase. The assumption being that by spending a little money up front on additional insulation, we improve the operating performance and cost of the building moving forward. And what we actually found out was that while there was a fairly noticeable on the peak week here that we're looking at, reduction between the peak heating loads between the 2.5 inch simulation and the 4-inch case, on the cooling side was almost a noticeable amount. Also within IES, we were able to look at aggregate yearly loads and take those numbers and go back again to our consultant to generate some numbers. And what we determined was that there would be an annual savings of about $290 per year by upgrading the insulation. So we decided not to spend the additional $12,500 that we would have had to spend on that additional insulation, which would result in about a 40-year payback, which is not something we decided to pursue. We did a similar series of simulations as well on roof insulation. And what we found when we looked at some of these peak periods was that there was a really very marginal reduction in the heating load between the two insulation thicknesses. And on the cooling side, it was even less noticeable when you looked at this graphically. Looking at it in terms of the overall amount of energy used, we actually looked at two different conditions. The one at the top, looking at the original constructed building that we were renovating, and actually only had 2 inches of insulation on it, and upgrading that to the code required minimum. We were able to determine that there'd be about a $4,200 per year savings in energy costs with that. Were we to increase that 20% further than that, we'd have less than an additional $200 above that. So again, having more than the code required minimum didn't seem to be the correct approach for us to take. And we looked at that also within the addition, and we had about $200 per year savings. So we decided to stick with the typical amount of insulation and forewent increasing the amount to a savings of $47,000 up front to the client. In general terms, looking at the loads on this building, what we found when modeling the entire project was that over the course of the year, in terms of BTU loads, in red you see the heating loads, and in blue you see the cooling loads on this particular project and the site and orientation. And in addition to the peak higher on the heating side. Aggregately, you see that heating really is dominating the operational costs of this particular building. Compounding that is also the fact that this is a university setting, and this particular facility is not expected to be in operation during the center months of the summer. That was particularly came into play when we were modeling performance of various glass systems on the building. We were looking into using a upgraded glass. We modeled a number of different glass types, but principally narrowed it down to two, one being a typical high-performance, low-E glass, and another one which we call a super high-performance glass, which, while having the same U value, it has a much better shading coefficient, which in the summertime, due to solar gain, will allow much less heat gain in through the window systems and create additional cool load onto the building. So in modeling that, what we did is we went into IES and were able to specifically model the actual products that we were comparing, getting some of this information directly from the manufacturers. We were able to create the exact glass buildups and performance characteristics that we're looking at putting in the building, and ran separate simulations after assigning those into the model. We were able to generate month-by-month loads, both on the cooling and heating side. On this side of the chart, we were generating for the typical low E, and on the right, the higher shading coefficient glass. And we did see a dramatic reduction in the cooling loads. We were able to drop it by 45%. On the heating side, we actually found that we increased the heating loads by 3.9% in the winter, where that solar gain is actually a benefit to the space. As you recall from a previous slide, the heating loads are dominant when taken on the aggregate over the year in this building. So in our case, the modest increase in heating loads more than canceled out the energy savings that we got on the cooling side. When we looked at it in terms of the aggregate amount of energy, it was 4,000 megabTUs, which on the face of it sounded very small, considering it's only about 0.5% of the building's energy consumption. That said, again, working with our consultant, we were able to show that that amount of energy, given our energy costs here, represented about a $2,500 a year additional cost to the project, and that would have been on top of the fact that we spent $200,000 to, in theory, upgrade the glass. So needless to say, we didn't pursue an additional upgrade in the glass. In addition to some of the overall building analysis, where we were looking at components throughout the building, we looked at some key elements and spaces around the building. Shown here is an entry pavilion into the building, which is on the quad side. It was intended to be a focal point for the entry of the building. It's also a major two-story space, a gathering space within the heart of the building. It also happens to be southeast facing, so we've got 2 stories of southeast facing glass, and the concern was that it was going to be, if not fairly uncomfortable, it would represent a fairly significant cooling load that if we could avoid, we would. So we looked at a series of different overhang configurations, ranging from 1-foot overhangs up to 7-foot overhangs, to see if we could justify the additional expense by way of any savings that might be realized. And what we found was that between a 1-foot overhang and a 7-foot overhang, there actually was a fairly dramatic reduction in the cooling loads on that side. We were able to reduce the cooling loads by 21%, which represented a significant cost savings to the university. On a related note, here's that glass entry pavilion that we talked about that we modeled specifically for looking at the overhangs. When we looked at the overall building performance for more global issues, IES, as part of that process, we were able to look at all the data aggregated into one graphic, like we have down on the lower left here, which looks at overall building performance, but within the same files, we can actually go in and look at individual spaces. And I happen to be looking at the overall building performance on the peak heating day, and noticed that there was actually some cooling demand at midday in this building. I was curious as to where that might be so we can address that situation. So I was able to go through room by room and in real time watch these graphs update room by room to see where the loads were. Identified that we have a southeast facing greenhouse. It's not really a greenhouse proper, but more of a botanical sciences laboratory. But it's southeast facing, very tall glass with no shading. And it was, as you see here, these lines indicate the heating loads early in the day. And then as the heat gain comes in, we actually got into a situation where they had a demand for cooling, and then later in the day, switched back over to a cooling load. So I was curious and looked back at our entry pavilion that we discussed before, and if you look at the same space, you have a similar pattern where the heating load in the morning drops off, but because of those overhangs, you never get into a situation where there was a call for any cooling during that winter day. So in addition to that, we were able to identify the greenhouse as a location where we wanted to add some operable lights to the windows so that we could avoid having to cool that in the winter months.
So continuing the theme of solar shading, part of the design of the building, really we wanted to inform through the evidence-based process. And we looked at a series of vertical and horizontal shades to try to ensure that we weren't making mechanical systems for a lab building, which by its very nature are working hard to begin with. We wanted to make sure that we weren't making them work any harder than they needed to. We wanted the building envelope to be part of the optimized performance of the building. So what you see here is a very simple model that we did. For some of our simulations, we didn't run the entire building model of the IDS, but we also built a series of these little vignette models to look at isolated issues. And so in this case, what we have is a west-facing lab and an east-facing lab. The large green rectangle is an architectural element that projects out the facade of the building, and we wanted to make sure that if that had any impact on the shading, that was being taken into consideration. And then we looked at a series of vertical and horizontal shades to try to optimize the right performance of them. So looking at what we did, started with the horizontal shades. We looked at a series of depths. This one is showing the 12-inch and the 36-inch. And the idea being that if we can eliminate some of the unwanted solar gain into the space, that we can take some of the load off of the cooling. This graph actually is an amalgamation of all of the studies that we ran with vertical, horizontal, no shades, and maps them all together to really kind of express a major point that is the focus of our goals here. When you look at the peaks, even the best, most aggressive, environmentally conscious engineer still is looking at peaks of load when they're sizing their systems. So if we look at some of these simulations, reducing a peak slightly, like these two simulations would have indicated, really have no bearing on first cost because you still need the full-size mechanical systems in order to be able to handle that peak load. And there may be a minor reduction in the operating cost. But what you really want to look for are the opportunities where you can dramatically lower the peak. If you can bring the peak down, you can bring down the load of the building, which means reduce first cost because you can downsize the air handling equipment, the chillers, the boilers, the other major pieces of plant. But you can also reduce the operating cost of the building. So as we move through our shading studies, looking to optimize, what we found was that for the horizontal shades themselves, we were getting good performance out of the 12-inch and really not a dramatic increase with a 36-inch. So the added cost for the deeper fins really was not warranted in our particular location. We did a similar study with vertical shades, the rule of thumb being that for a west-facing lab, vertical shades should work better. So we ran a series of simulations of shallow and deeper fins, and when we got our results back, what we found was there actually really wasn't that great difference between the 36 and the 8-inch fin, and we were getting better shading out of the horizontal. Partly, I think it was due to the fact that the horizontal shades were allowing in the winter sun. So this is actually a bit of a trick slide. We're not looking at cooling plant in this particular slide, but the heating plant. And I think one of the key points to take away there is, as you may be looking to isolate one variable, like looking at a reduced cooling load, you need to make sure that there isn't an unintended effect at the same time. So we ran cooling simulations. But then as we focused in on the fact that we were being driven by heating loads, we made sure that there wasn't an adverse effect by the same device. And so when you plot all these things out together through IES, you're able to get a series of different iterations that you can look at and compare. And so as we see for cooling, having no shades was the worst scenario, both in the east and the west facing. If we're looking at the heating side, then having vertical and horizontal was the worst because we were blocking out the beneficial sun. And so by mapping on a series of iterations, it gives you the ability to start fine-tuning different orientations of the building and optimizing the shading devices that are going to have the best and most effective impact on the building.
We also did a number of studies looking at some of the typical spaces within the building to evaluate the amount of usable daylight we could count on, given the glazing we ultimately selected and the orientation of the various spaces, with the aim to see if we could benefit from controlling the interior lighting. At the upper right, you'll see an image that shows 2 out of the 3. There's the 2 white lines at the top are layers of lines of lighting. The third line of lighting isn't shown because it's turned off, and the daylighting coming through the window actually results in a fairly even illumination through the space. So looking at that, given the typical sections of these spaces, again, you can see the 3 lines of light. We wanted to also evaluate whether the addition of light shelves would increase the penetration deeper into the space so we could get more usable light throughout. And initial studies showed that we could get a fairly good amount of usable daylight for pretty much the outer half of the lab, and did further investigations based on the outer 2 rows of lights. And down below, you can also see the types of outputs we were getting within IES Radiance, one being a more graphical view, in which case, you can look at a couple of sample points and see that the lighting level was actually reduced when we added the light shelves, as well as when you look at some of the point readings. The point readings within this module, you can control the density of that grid and how it outputs, and what we did is control that so that we were getting point readings that were corresponding to the lines where the actual light controls were going to be, the actual rows of light were. So looking at the further without the light shelves, how we might control the various rows of lights within the space, we wanted to see what types of controls might make sense so that we could get the best performance out of our artificial lighting, given the natural lighting. And what we did is within the Radiance program, we placed theoretical light sensors within the program that corresponded to those rows of lights where we would theoretically have a light sensor that would control the dimming on these. And then what we were able to output was for each of those sensor locations what the actual illumination levels would be at a lab bench height for each hour of a day within every month and every day of the year. And one thing that we saw was that there was a lot of usable light at the outer row of lights and a fairly good amount of usable light at the second row of lights, but significantly different levels. So even just that alone showed us that if we were going to do light sensing controls, it made sense to independently control both of those layers of lights, which is something that we did spend to put into the project. We also then took the light levels that were generated from that and compared them against the recommended illumination levels for a laboratory during the times of day and the days of the year that they were actually operating the lab, and we determined that 28% of their daytime lighting needs in the lab overall, even accounting for the third row of lights that we weren't controlling at all, 28% of their lighting needs could be met using natural daylight.
So hand in hand with the daylight harvesting that we wanted to make sure we were maximizing, we wanted to be sure that the artificial lighting was also optimized. Being a northeast climate, all through the winter, it gets dark quite early, and there are many times of the year where there is no availability of daylight, and we wanted to make sure that the light levels were being met and that they were functional, but also that we weren't overlighting the space. Early on in DD, we had developed a kind of architectural lighting idea, which you can see in the middle diagram, that had a series of direct, indirect pendants forming a kind of architectural road that gave some shape and definition to the space. We hadn't fine-tuned the total quantity of the lighting early on in the DD phase, and when we started transitioning from DD towards construction documents and started looking at that more closely, we started looking at a space-by-space basis. We set up a series of individual room models so that we could look at each prototype of space, whether it be an office or a lab or conventional classroom building, and optimize it on that one space, and then use the lessons learned there to apply to all the other similar kinds of spaces. Interestingly, what you can see right off the bat here is that the mass energy code baseline is 1.4 watts per square foot, and our initial lighting layout was 3.71, which is well over the allowed limit of that particular space. On aggregate, we were actually right on for the entire building. Our electrical engineer had to run a check for the code, and we were right at the code baseline, but we certainly wanted to do much better than that. We set a target for ourselves of trying to do 30% better than what we'd be allowed to do, and so we used the IES tools to go in and start going space by space and analyzing those. And we ran a series of iterations for each one, and in the case of this conventional classroom, we worked out some more of a gridded arrangement of lights. And what we were able to do was to find that we were able to hit the average right on the target, and we were able to bring down the power density for that space down to just under a 1 watt per square foot, which is even better than the code reduction limits we had initially set for ourselves. On aggregate for the whole building, by the time we went through all the spaces and incorporated lighting revisions, we did just better than our 30% reduction. We had set a target for ourselves. And so what this resulted in then is significant first cost savings, because we just flat out eliminated quite a number of light fixtures that we previously had in the design. But we also reduced the operating cost of the building by having fewer lights. In addition, by hitting that 30% target, it wasn't arbitrary. That was very much focused on some potential energy incentives and things that the university can realize now by hitting those levels. So it was a very useful tool for going through and really fine-tuning the design and hitting some targets that we had set for ourselves.
A little more complicated features that we looked at within IES that actually used a number of the different modules was a study of the stair tower. You can see the Revit geometry of that here at the upper left rather. And this is a southwest facing stair, and at this particular face of the building, it was trying to be a new entry to the campus, and it wanted to be a major architectural feature, something to be seen glowing at night. But there was concern that, given the extent of glass, that the stair would be extremely uncomfortable, and typically these stairs aren't something that would be conditioned by mechanical means. If they were, it would represent a fairly significant load. So at the suggestion of a mechanical engineer, we wanted to look at whether we could utilize the stack effect within the stair to naturally get out some of this excessive heat gain, and that possibly we could keep the interior temperature from rising no more than 5 degrees above what it was at the exterior. So using the SunCast module, we modeled and captured all the heat gain calculations throughout the year, and then using the macro flow, the sample image at the left here, we looked at a number of different types of configurations on how we might add an opening low in the stair and an opening at the upper part of the stair to be able to effectively vent that space. We also looked at a number of different control programs, when this should open it open up before the temperature got to a certain point, when they should close, different types of louver sizes, and we ran a number of simulations to show that. And in terms of the output, what we did find was that what you see in red here is throughout the year the exterior temperatures, and you get the cooling loads throughout the year, the building energy loads throughout the year. We did see a significant savings there, and typically on the peak week, peak month, and the peak day, we did manage to keep the stair temperatures within 5 degrees of the exterior temperature. What's, I think, a little more dramatic than that is what we did is IES allowed us to set threshold and sort the data based on that threshold, and I could track how much of the time we would go above 72 degrees within a stair, which is a common cooling set point that people would use. And we were able to determine that just by naturally ventilating the stair, we would cut the amount of time that the stair ever went above 72 degrees in half, so that less than 10% of the time that stair would go above 72 degrees. So had we decided to address this problem with artificial cooling, which we probably would have had to because the stair was getting up into the high 90 degrees, we would have had to buy additional capacity in our cooling system to the tune of about $34,000.
So I think looking at this in its total, what are our lessons learned? We had a project team right from the owner down through all the consultants who were really committed to a high-performance building and optimizing energy reduction. If we'd been doing this project about 5 or more years ago and not had some tools like IES available to us, we would have gone in willingly trying to spend money to save energy, and we could well have done a number of things that the rule of thumb says are a wise thing to do, but having run the simulations, we would have been putting money in that really had no payback. So just for the things that we looked at alone, and this is independent of all the things the mechanical engineer was doing to create mechanical energy savings, we could easily have spent about $1.5 million on a variety of things that sound good, sound prudent, sound like energy conscious and sustainable approaches, but when you actually boil them down and look at it, that there's maybe a more effective way of addressing the exact same issue. And so in addition to the first cost savings, which you're then able to put directly back into the programming and benefit directly the people who are using the building, on top of the savings that the mechanical engineers were realizing, for these things we studied, the building performance itself was able to reduce the building energy annual consumption by about almost $35,000, $34,000 a year. So what do we take away from this? What are the lessons learned? Initially, although we focused mostly on the energy modeling simulations we ran today, it really relies on all of the key party members setting goals, sharing goals, and agreeing early on and contributing and collaborating to make sure that those goals are realized throughout the design process. Number 2 is that if you want to do better than a rule of thumb building, then you can't rely on manufacturer data or assumptions that because something's more expensive, it's necessarily better to do. You really need to do specific simulations that are specific to your project and your location and specific to the way that the building is going to actually be used. And then third, in order to have the data available to you to make informed decisions, you need to do continuous experimentation throughout the design phase and make sure that you have the feedback when you need to make those key decisions and not 6 or 8 months, 6 or 8 weeks after the fact. So with that, we'd like to thank you for your interest today. We hope you've learned something and appreciate your time.